But I kind of think the same.
Okay, so I'm sorry I was away, a little unconscious. I got back from Berlin last night, so we'll do our best. Okay. So where were we? We were on the definition of the Adels and the Edels. So remember, we have a number field, K. And last time we showed that there were many different completions of K. So we had real completions, and we had maybe complex completions, and then we had p-adic completions. So there were infinitely many completions. And inside of if V corresponds to a finite prime P, so these were completions that were defined by adjoining the limits of Cauchy sequences with respect to evaluation. So adjoin limits of Cauchy sequence, just like the way we get the real numbers from the rational numbers with respect to evaluations, which were homomorphisms, so in case certain different homomorphisms to the positive reals that satisfied a triangle law. All right, if B corresponded to a prime P, and in that case the valuation of alpha B was the norm of P, was normalized to be like this, minus word of alpha, then this completed field had a little bit more structure than in the real or complex case. Namely, it contained a subring, AB, of all of alpha such that the evaluation was less than or equal to 1. And that was because when you added two things, evaluation less than or equal to 1, you got something evaluation less than or equal to 1. Okay, and we saw this contains the ring A, because anything which is an algebraic integer has positive value ordinal for every finite prime. Okay, so the idea of defining the Adels is to define something between the direct sum of all kV and the direct product of all kV. Here, in this, almost all the terms are 0. Here you can choose arbitrary elements in the completions. And you want to have two things about it. First of all, you want it to contain the field. And that's true here, and not true here, because an element in the field isn't 0 at almost all completions. So it has to be larger than the direct sum. But the problem with the direct product is that every one of these completions is locally compact. This is locally compact in the metric topology, namely has compact neighborhoods of each point. And this subring is actually compact because in the metric topology it's the alpha such that alpha is absolute value less than 1. So you'd like the Adels also to be locally compact. And the brilliant idea of doing that, which was originally due to Chevalley, is to take what's called the restricted product of the KVs, where almost all of for each Adel, almost all the elements in the direct product lie in these subrings. So it's an Adel looks like this, with almost all AB. Now, of course, you can't define what AB is at the finite places, but there are only finitely many of these. Namely, last time we saw there are R1 plus R2 infinite completions. And so you don't pay any attention to those, and you just say at the finite places, almost all. And the reason that contains K is that any alpha A and K has only finitely many denominators. So when you think of it locally, it's in AB for almost all V because the integral elements are in AB. And the reason that this is locally compact is that it can be written as a direct limit It's the union over all S finite set of V containing the infinite places of the product over those V of KV cross the product over the V not in S of AV, right? If you take the union over all S, all finite sets getting larger and larger, any Adele sits in one of these finite sets because almost all the places are integral. And this product is compact in the product topology by the Tikhonov theorem, and this is a product of a finite number of locally compact spaces, which is locally compact. And so the whole thing is, this is locally compact neighborhood, and they exhaust the locally compact neighborhoods. Okay. Now, the big theorem, we'll do the first theorem, is that if we embed K into A, is a discrete subgroup in the induced topology. So there's an open neighborhood of A that contains only one point of K for each point of K, and the quotient group is compact. So this is just like, you should think of this as like the integers embedded in the real numbers, or more generally, the ring of algebraic integers embedded in K tensor R. These spaces are locally compact abelian groups. These are discrete subgroups. There's a lattice inside of this, and the quotient is compact. All right, so here's the proof. Let's do the proof. Okay. And it's the opposite, by the way. Let me just say, it's the opposite of AV included in KV. So a typical case of this would be like putting ZP into QP. Okay, so ZP is compact in this locally compact space, and the quotient group is discrete. This is the direct limit of Z mod P to the NZ, or maybe I should write it as P to the minus NZ mod Z for all N. And so it's a direct limit of finite groups, so it's a discrete group. So here you have compact and locally compact with quotient discrete. Here you have discrete in locally compact with quotient compact. Okay, let's do it. All right, the first thing, proof, is that the claim is that the Adeles, any Adele can be written as the sum of some element in K and some element in this subgroup. So you have two subgroups of A, K, and the product over V dividing infinity of KV across the product of V finite AV. So this is a very natural subgroup of the Adeles. It's sort of the largest element it's the smallest element we can make in this, because our finite set has to contain the infinite places, so we just take the finite set to be the infinite places. So this is clearly a subgroup. If I have Adeles of this form, that means they're integral everywhere. And I also have the subgroup of elements from the field. And any Adele can be written as the sum of an element in the field and something which is integral everywhere. And moreover, the intersection of these two groups, so I'm going to show you this. That intersection is just the ring of integers of K. So you can recover the ring of integers because this is just an element in K whose valuation is less than or equal to 1 at all finite places, and that means that no prime divides any denominator, so that's what it means to be an integral element. So you have two subgroups, this subgroup and this subgroup, and their span is the entire ring of Adeles, and their intersection is the ring of integers. Well, this is clear. Why is it true that any Adele can be written that way? Well, take your Adele and modifying it by an element in this, how do we get it into this subgroup? Well, our Adele, which is AV, has only finitely many denominators. And it may not be in this subgroup, but it only has finitely many denominators. So say the primes where it has denominators at primes, say, pi. And suppose the ordinal at pi is minus ni, or v of av is equal to minus ni, let's say pi of a pi is minus ni, right? You know, that's less than 0. Okay, so if we're able, suppose we can, what we claim is we can find an alpha in K with alpha mapping to the, so you can write AV as an element, something in pi to the minus ni mod AV plus something in AV. So its denominator is a class in this quotient, right? And then you have something which is integral. So suppose I could find an element alpha in K that mapped, and this quotient here, which looks like a local quotient, is the same as p to the minus ni a. Because last time we showed that when we looked at this local ring and we took AV modulo powers of its unique maximal ideal, which happened to be principal, that was the same as a mod p to the ni. So this principal part, you might say, of this Adele can be viewed as an element here, and I claim that we can find an alpha in K which maps simultaneously to all these principal parts. Well, that's the statement, really, that the map from K to the product over a finite number of primes of pi to the minus ni a is surjective. Right? That's the claim. Well, that's related to the Chinese remainder theorem that says A mapping to a product over a finite number of primes of A with pi to the ni is surjective.
Is this a strong approximation?
This is actually called weak approximation, but it's an approximation here. Yeah, it says that any collection of principal parts can be approximated by an element in K up to something integral. And the proof that this is surjective is basically the property that pi plus pj is the ideal A. So if you've ever done the Chinese remainder theorem in the classical case, you can prove it in this case too. And it follows that this is surjective. Now, this element alpha that you use to correct the principal parts, you might say, well, if I subtract alpha from A, I get an element in here. But that's not quite true because you may have created some denominators in alpha at other primes, but suffice it to say that you can correct those denominators. So I'll let you worry about this proof that this is the direct sum. But the key thing is this statement here. Okay, well, suppose we have that. Oh, so let me just make another claim about this surjectivity, because many of you may have seen that Adels are also a very good way to study algebraic curves. And in particular, algebraic curves over finite fields give you Adels that are very much like the Adels of number fields. So suppose, let's do a little aside on that, because that's an interesting point for those of you doing algebraic geometry. Suppose you have X, an algebraic curve, over the finite field F, which is FQ, finite field of Q elements. So the projective line, or an elliptic curve, or another curve, non-singular projective curve, and then you have a field, which are the function field of X. So all meromorphic functions on X, you should define over that finite field. And that plays the role of a number field. This is called a function field over a finite field. I mean, this works. Okay, Or you could do function field over C. I mean, people study those. So for example, if X is the projective line, then this field would be just rational functions in T. And if you had an elliptic curve, this function field would be like rational functions in X and Y, where they satisfied some equation like y squared is f of x. Okay, now this field also has completions. For every closed point on the curve, you get a valuation, or prime ideal in the integers here. You get valuations of k correspond to orbits, Galois orbits on points over the algebraic closures. So those are all closed points. And you can take the completion with respect to that valuation. And since any function on your curve only is regular at all but a finite number of points, only has finite number of poles, then you get an embedding of k into the adels of this function field, which are the kv over av. And this here we have av defined for all places. And that's the ring of functions, local functions, which are regular at the place V. And in fact, these completions are very simple fields. They're just Laurent series over a finite field. So this is fq to the degree of your point x, Laurent series. And this is these are the just Taylor expansions where you don't have any poles. And you have your field, you take your function, you look at it locally, it's given by a Laurent series, which is actually a Taylor series at almost all points. And so you get an embedding of k into the adels. And again, you prove that it's discrete, as has finite intersection with the product over all V of AV. So these would be the functions that are regular everywhere at every point of the curve, right? And the intersection of that with the global function field is just the constants. If you have a function regular at all points, right? So the finite intersection is just the field F, which we've assumed is finite. So that's a discrete subgroup. And again, the quotient is compact, but you don't have quite this direct sum. Namely, what happens in that case is you have a subgroup just as before. So k plus the product over all V of AB is a subgroup of the adels. And it turns out to be a finite index. And since this is compact, that's enough to prove that this is embedded as a discrete co-compact subgroup. But the index isn't always 1. And that's an important theorem in algebraic geometry. In the case where you have the projective line, in this case, every adel can be written as an integral adel plus an element in the field. That's the statement that on the projective line, you can find a function that has the same principal parts at a finite number of places as any Laurent series, right? By methods of, what do they call it? You do this when we teach integration. Partial fractions. Okay? So, but the index is not, so the index is equal to 1 for k is f of t, but not equal to 1 for other function fields. See, this is a more difficult question because here we had the infinite places to do anything we wanted with. But here, it's the product over all V here. And the difference, for example, for this elliptic curve case, it's impossible to find a global function which has a simple pole at infinity and no other poles. But there'd be an adel, right, which had a simple pole at one place and was regular everywhere else. And so it turns out that this quotient group is isomorphic. Quotient A modulo K plus the product of AB is isomorphic to the cohomology group of the H1 of the sheaf of functions. That's the first appearance of cohomology in mathematics, was the inability of 19th century mathematicians to solve the problem of principal parts on elliptic curves. And they realized that there was an obstruction to it, and the obstruction is cohomology. And this is a vector space over F of dimension G. And since F is a finite field, this has order, Q to the G, where Q is the number of elements in the finite field. If it weren't over a finite field, if you tried to do this for an algebraic curve over C, first of all, this isn't locally compact. And secondly, this index is not finite, because you get, again, the solution of principal parts, which is a finite dimensional complex vector space. But over finite fields, it works perfectly. And notice how cute this is. You see, the intersection of these two is F. And the index is a vector space F to the G, where G is the genus of the curve. I'm sorry. That's the definition of the genus of a curve. So if you wanted to define the genus just by doing Adels, and they did the entire theory of algebraic curves using this point of view of Adels, the genus would be the dimension of this vector space as a vector space over the field of definition of the curve. Okay, and if we wanted to calculate the volume of this compact quotient A mod K by putting a measure on it so that this open compact subgroup had volume 1, what would be the volume of A mod K? Well, the quotient, this would have volume Q to the G, but there's an intersection of one copy of F. So the volume of A mod K would be Q to the G minus 1, right? Which is, in some sense, half of the norm of the canonical class. Equal to the square root of the norm of the degree, or the degree of the canonical class. Well, I don't know how to write it. Namely, the canonical class has degree 2G minus 2. You take Q to something like that. And we're going to see this plays the role, this Q to the G minus 1 plays the role of the square root of the discriminant in the function field case. And we're going to see that the volume of A mod K in the number field case is related to the size of the discriminant. Okay, that's a little detour. But as I say, in the number field case, the difference between number fields and function fields is you can't take the product over all places of AV. This is sort of the smallest reasonable subgroup you can define. Whereas in the function field case, you can define the product where it's integral everywhere. Okay? Anyhow, it's good to know where cohomology first came up, and it was solving this principal parts question of curves. And mathematicians like Abel and Jacobi were puzzled by the fact that they couldn't find a function on an elliptic curve that had a simple pole at infinity and no other poles. Okay, so let's continue now with the proof that the quotient is compact. Once we have this, first of all, it's clear then that K is discrete. The reason is that the intersection with this subgroup is the ring of integers. If I wanted to intersect with an open subgroup, I could take this product, and inside every place at infinity, I'd make an open subgroup of KV. Like I take an interval, a small interval over the reals, or I take a small circle over the complex places. So that would say, and the intersection of that would be the integers which have bounded real parts and bounded complex parts, right? But there are only finitely many algebraic integers at that site, because if you bound the size of their embeddings at infinity, then you bound the coefficients of the characteristic polynomial, which are made out of symmetric functions of that. And the coefficients characteristic polynomial are integers. So you have a bounded number of integers in any real interval. And so that shows that the intersection of A with this open subgroup is finite. And if I made these things small enough, it would be just 0. So that's the discreteness. How about the compactness? Well, we have a map from, if I divide by K and I use that direct sum, that's the same as the product of the KV divided by infinity cross product of the AVs divided by the intersection of this with K, which is the ring of integers. So equivalently, I have to prove that this quotient is compact. All right, but this product is compact by the Tikhonov theorem. So I have a map with compact fibers down to the product of all the KV modulo the image of A, just embedded in the complex places, right? And this is the same as K tensor R, modulo the image of A. And that is compact. This is a compact fibers. This is compact by the existence of, by the fact that the discriminant is non-zero, which shows that if you choose a basis for A, alpha 1 through alpha n, and you embed that into this real vector space, you get a basis for that real vector space. And so that's the non-vanishing of the determinant that defines the discriminant. And so that says that this quotient is compact and is isomorphic to n copies of the circle. R mod z to the nth power. And that's the quotient being compact. Okay, that's the discriminant. Now it gets much more interesting and also more complicated when we do the edels. So that's the next statement about locally compact groups. So the edels are the restricted product of the multiplicative groups of the local fields where almost all the terms are in absolute value 1. So remember, these are the alpha b not equal to 0, and this is the subgroup at finite primes where the absolute value of alpha b is equal to 1. So not only less than or equal to 1, that would be an integer, but you need it to be invertible, so that means it has to be, its inverse also has to have absolute value less than or equal to 1. Okay, and again, we have an embedding of the multiplicative group of the field for the same reason that we did last time, namely an element here has only finitely many denominators, and so at almost all places it lies in here. Okay, and we have a norm map from the multiplicative group of the edels to the multiplicative group of positive real numbers, which I claim is surjective, the norm homomorphism that takes an AV and it takes it to the product over all V of the valuation of AV. So almost all of these are 1, because almost all terms for each edel lie in the AVs. So this is a finite product. And it's clearly a homomorphism because each of the valuations, sorry, I keep changing from A to alpha. It's a homomorphism. It's surjective because I can put anything I want at a real or complex place. And if I just put that at a real place or complex place and put 1 everywhere else, then this product is just that valuation at the real place or complex place, and you can get any real number, right, as a valuation. So it's surjective. And moreover, the kernel contains this subgroup K star, kernel of the norm contains K star as by the product formula. We saw that. That was how we normalized our valuations at finite primes so that that finite product was 1 for an element in K star. And so we have an embedding. That's our next theorem. K star embeds in the edels, let's call them the edels of norm 1, the kernel of that. Let's call that K star 1. It embeds as a subgroup, it's a discrete subgroup, and the quotient on K star is compact. We're going to prove that. So that's analogous to what we have in the edels. The only difference is that it's impossible for A star mod K star to be compact because it surjects onto this group, which is isomorphic to the additive group of real numbers, and that's another compact group. Okay? So this is more interesting because it's not the non-vanishing of the discriminant, but it's the, I still have to prove that, sorry, before this, I got ahead of myself. Want to show that the multiplicative group of the dells under this restricted product topology is locally compact. So we have to say a little bit about the topology of the completions. So we give KV star, which is just KV minus 0, the induced topology. So it's metric topology. And then inside of this, we have the local units, which are the things at finite primes where the absolute value of alpha is 1. And in the metric topology, that's a compact set. It's also open because I could say it's the absolute value of alpha that's bigger than 1 over Q and less than Q, because the valuation is discrete. The only possible valuation inside of this interval is equal to 1. So this is the compact, and this is the open. And the quotient is discrete. In fact, the quotient, we have an exact sequence locally. You have the local units, they map to the local field elements, which are non-zero, and by taking the ordinal of something in here at B, you get a map to the integers. It's surjective because we saw we had an element pi in here, which had v-adic ordinal 1. That's a uniformizing parameter. And the kernel, the things which have ordinal 0, are precisely the units. So the quotient is this discrete group, just like we had for the, but it's a simpler discrete group than, say, QP mod CP. Okay. Okay, now this, unlike the additive case, this is a very interesting situation where this group is locally compact and it has a unique maximal compact subgroup. Unique maximal compact subgroup. Locally compact. The reason it's maximal is if you had anything which had valuation which is either greater than 1 or less than 1, like valuation Q or valuation 1 over Q, then taking powers of it, you get all the different valuations, and that can't be compact. And that's very different, if you think of it, than the additive group. In the additive group, we had an open compact subgroup AV. But it isn't maximal because I can multiply it by any power of pi and get another open compact subgroup. So I have a whole sequence, AV, which is contained in pi inverse AV, which is contained in pi to the minus 2 AV, etc. And that contains, etc. So a whole chain of open compact subgroups. Whereas in this case, there's a maximal one. And it is filtered by open compact subgroups. And how do I filter it? And this is, if you're going on and do reductive groups, the difference is that the multiplicative group, GL1, is a reductive group, and the additive group here is not a reductive group. So it turns out that for reductive groups, when you take, if G is reductive, and we'll get there maybe later when we do some automorphic forms, and you take the points of G and KV, like GLN over KV, something like that. So this is always locally compact, and it has maximal compact subgroups. So for example, GLN of KV contains a maximal compact subgroup, which is GLN of AV, the matrices that have integral entries and determinant the unit. That's not the unique maximal compact subgroup, but there's a maximal one, whereas in groups like this, KV, there are whole chains of open compact subgroups. Okay, and by the way, how do we how do we filter A star? Well, I claim that A star has a subgroup of the things of the form 1 plus pi AB. So this is the elements which are units where when you reduce the mod pi, you get 1. So this is the kernel of the map from AB star to AB mod PV star. So things that are 1, this is the same as A mod pi. So I write it like that because the kernel is the element 1 mod PV, and that contains the subgroup 1 plus pi squared AB, and that contains the subgroup 1 plus pi cubed AB. So these are the things that reduce to 1 modulo PV squared. These are things that reduce to 1 mod PV cubed. And that's an exhaustive filtration because any element, if it reduces to 1 mod all powers of P, it's equal to 1. So the intersection of all these groups is the identity, and the index is finite because it turns out that this map is surjective. So this group is like A mod P star, which is the multiplicative group of the residue field. So that's a cyclic group of order Q minus 1. And then all of these groups are the additive group, are isomorphic to the additive group of A mod P. You see if you can prove that. So you get a filtration of the multiplicative group of local units by subgroups of finite index, which is an exhaustive filtration. And that's another way of showing that this group is compact because it's profinite limit of all the quotients. Okay, so this is the limit of AB mod PV the n star, and all of these are finite groups. And these also have beautiful filtrations just like this, like you can take the matrices 1 plus pi and n of AV and 1 plus pi squared and AV. So when people realized that they wanted to do non-abelian things, they took the theory that Tate had developed for GL1, these subgroups and their filtration, and they used them for GLN in the same way. Right? This is perfect analog of this, and then you get this analog of that, etc. Okay, so that's the local groups. Now again, I claim that the edels are locally compact because, for exactly the same reason, namely their union over S, same type of S, but now we take the product over V and S of KV star cross the product of V not in S of AV star. Any edel has only finitely many denominators, and if S are the places where it has denominators, it lies in this subgroup. And each one of these is locally compact because these are locally compact and this is a finite product, and these are compact, so the infinite product is compact by the Tikhonov. So that's the locally compact statement. And now we have to do the discrete subgroup and the compact quotient, which are more serious. All right, why is K star discrete? That's always easier. K star in A is discrete. Well, again, we have to find some neighborhood of the identity that intersects K star trivially. Well, sorry, this is AB star. Well, let's take the subgroup. There's a canonical subgroup just like there is in the edels. U, let's let U be the smallest one of these. So the product over KV, V dividing infinity star, plus the product of V finite, AB star. Well, clearly U intersect K star is A star, right? Because if something is got valuation 0 at all finite places, it's a unit. Okay? Now that's not a finite group, but if I took a neighborhood at all the infinite places, so I took a small neighborhood of 1, maybe UV of 1, then again, the intersection would be finite because I know it was a unit and I know that so it's an algebraic integer, and I know that its valuations in infinity were in some interval around 1. And so there are only finitely many algebraic integers with that property. And by the way, okay, so that's at least the intersection, and if I take an open, small open in U, intersect K star equal to finite. That's the discrete proposition, but the compactness is much more interesting. So notice that the quotient of the E-dels by this subgroup U is familiar to us. That's the ideals, and that's why Chevrolet invented the E-dels. So notice that we have an exact sequence because to give an E-del modulo this subgroup is just to give an element in KV star mod AV star for finitely many V. So that's to give an integer for finitely many V, and that tells you what the ideal is, right? Take the product over those primes where there's a denominator, PV to the order VAV. So just take next element AV, and take it to product over V, finite V, where AV is not in AV star, or PV or AV. And that surjects onto the ideals because I can make locally an element that maps to anything. And the kernel are the things which have trivial valuation in all finite primes. It can be arbitrary infinity. Okay, so therefore, suppose I take the quotient by a little bit of a larger group. Suppose I take suppose I map U into, instead of taking all the E-dels, I take the subgroup that I get by multiplying elements in U by elements in K star. So that's analogous to this thing we did in the ADELs, where we did the subgroup K plus the product, that sort of thing. Here we multiply elements in this large subgroup by elements in the field. Well, then when we map to ideals, we don't get all ideals because the only denominators are coming from elements in K star. And so they map to the principal ideals. Because principal fractional ideals, because you're only getting these products where that's equal to the products of some alpha in K. Okay, so that says that if we take the quotient of A star by this subgroup K star U, and we use, so we have little arrows here. This is the identity map. And so the quotient here is the quotient here by the state lemma, and that's I mod P. So that's the class group. And in particular, this has finite index in the E-dels if and only if the class group is finite. And we're assuming that we prove that somehow or another. So that to prove the compactness of, and what's the intersection here? The intersection is precisely the units of A, right? Because it's an element of the multiplicative group which has valuation 1 in all finite primes. So since this is a finite index in A star, to prove that K star is a compact quotient in A star norm 1, we have to show, we're now reduced to showing, that if we put K star in K star U, okay, so we have therefore an exact sequence U modulo A star goes into A star K star, which goes to A star K star U 1, and this is finite group. Right? So the intersection of U with K star in A star is A star. So this is the kernel of this embedding, of this map. And since this is finite, to show this is almost compact, it suffices to show that this quotient must show that this is the product of the compact group and one copy of the real numbers. I mean, we could also do this with A star norm 1 and eliminate the real numbers, but to show that it's co-compact in this group, it suffices to show that this quotient is compact with an extra real number. Okay. Okay, so on the other hand, this group maps, again, with compact fiber, because this group in U, I've erased U already, but U was the product of the over V dividing infinity of KV star across product of AV star. And this group is compact, so ignoring that compact fiber, this group maps down to the product of KV star modulo the image of the unit group. Okay, now that's, now this KV star is V dividing infinity. Well, if we take C star, that's the product of S1 with the positive real numbers. And R star is the product of plus or minus 1 with the positive real numbers by taking evaluation. So we can again ignore these groups which are compact and map it with compact fibers to, I'll call it R to the R1 plus R2 modulo the image of A star under log of the absolute value of V. Because if I divide out by these compact groups, I get a copy of the positive reals, and under log of the absolute value, I get a copy of the real numbers for each valuation. So the product of these gives me R1 plus R2 copies of the real numbers, and then I have the image of the units in there. And that, we saw, was almost compact because the image of the units lie in a hyperplane, and they form a discrete co-compact subgroup of that hyperplane. That's the unit theorem, so this is compact cross R. And that encompasses not only the unit theorem about the rank of this group, but the fact that it is discretely and co-compactly embedded in the real places. And again, one proves that by traditional methods in number theory. So the compactness of this quotient turns out to be equivalent to the finiteness of the class group. You might say, well, wait a minute, I didn't need the class group to be finite in this argument. I just needed it to be compact. But in fact, since this is open in the Adels, the quotient will be compact if and only if it's finite. So you need the finiteness of the class group, then you need the rank of the unit group, and then you need the regulator to be non-zero. So this is basically HR non-zero, that sort of thing. And of course, once people realized that these statements about the Adels and the Edels were equivalent to all these classical things in number theory, they decided, well, I could prove those classical things by just doing an Adelic argument. And you'll find such an Adelic argument in many books like Bayes' book, Basic Number Theory. And that way you can recover all the classical theorems in number theory from these two very nice statements. I realize there's a clock here. Good. Okay. Good. Now let's take a look at the Edels for the rational numbers, because that's very indicative of where we're going next. So if the rational numbers thing simplify, because the unit group is very simple, it's just plus or minus 1, and the class group is very simple, it's trivial. So for k equal q, A star is C star, which is plus or minus 1, and the class group is the trivial group because it's a principal ideal domain. It's almost that simple for, say, the Gaussian integers. It gets more complicated as we go along. So what does A star mod Q star look like? Well, by the analysis we just had, we had that subgroup U, which is R star cross the product of CP star over all primes P. Then we have to divide out by the intersection of this group with Q star. The fact that this group union times Q star is all of the adeles is the fact that the class number is 1. And then when we divide out by the intersection of this group with Q star, we just have to divide out by the image of Z star, which is just divide out by plus or minus 1. Now, if you want to, what you can do is say, well, I'll just modify the real number in this factor by an integer unit to make it positive. So this could be written as the product. It's a little less nice this way, but you could write it like this. Right? It would just be this group. And there you see, here's compact, and here's one copy of the real numbers. Okay? But this group, CP star, is the inverse limit of Z mod PDA Z star. And this whole product is actually, so this is equal to R star plus cross the inverse limit of Z mod NZ star over all positive numbers n indexed by divisibility. And then you get, if you just, because this, if you take n the product of 2 primes, you get the 2 products here. Okay, so if I ask you what are the continuous characters chi from A star mod Q star to C star, those are called Hecke characters. Characters are the adeles that are trivial on the rational adeles, and continuous with the topology here. Well, if you here you can have any character. This is a product of things, so you can have a character of this times the character of this group. Now that's a profinite group, and so it's arbitrarily small open compact subgroups, and C star doesn't have arbitrarily small open compact subgroups. If you make a small open subgroup around 1, it only contains 1. So if you have a continuous character, it's got to be trivial on some open compact subgroup here, which means it's just a character of one of these Z mod n stars, and it has a modulus. So the continuous characters have the form, I'll call them chi S times the character of Z mod NZ star for some n. Maybe I'll call this chi F or something, because that's the finite part of the character. Where S is an arbitrary complex number, because if I want to take a real number, if I want to study the characters of this group, they have the form T to the S. For, T goes to T to the S. So the continuous characters of this quotient are given by 1, a Dirichlet character, and 2, a complex number. Okay? So you might think that associated to chi, which is chi S times chi F, we'd associate the Dirichlet L function, L chi F, at S. Right? That's what we've been studying, a thing that evaluated a complex number. And that's what we're going to do. We're going to call this thing, Kate's thesis, this is just called L of chi. And we're going to see that for every character, every chi of A star mod K star, we will define a complex number. Well, you have to worry about the trivial character, but I'm going to leave that for the moment. L of chi, which is going to be a value of an analog of a Dirichlet L function at S. And we're going to prove a functional equation relates L chi to L chi inverse times the edelic norm. Notice that the edelic norm is a continuous character. The norm maps A star mod K star to positive real numbers. So that's a subgroup of C star, and it's continuous, right? So a particular example of an edelic character is the norm. And notice that this chi-s here is just the norm of the edel to the s power, because all of these edels have norm 1. So in this formulation, the norm of an element in this quotient group is just the norm of this real number. So this incredible realization that for the rational numbers, the characters of the edels modulo the field elements were really just Dirichlet characters together with a complex number, so you could define a complex L function. And the functional equation relates the inverse character at 1 minus s. Well, this turns out to be just the character, this is the complex number 1, right? And this would be a minus s because chi inverse would be chi of minus s times chi of f bar, because this is a finite order, right? Okay, so we'll get there, But in the meantime, let's, yeah, we have some time. Let's do the local characters before we get to the characters of the edels. Because remember, the edels themselves are a product. So we can get a character of this product group by making products of local characters. So that suggests that we figure out a little bit of information about characters of the additive group of local fields and characters of the multiplicative group. I'm running out of long pieces of chalk. So there may not be any more lectures in this course unless I can find another box of chalk. I am not a person who likes to lecture with a piece of chalk. A lot of people prefer to lecture. No, Lena, you don't have to get any more. For the next lecture, I have one more piece. Once this piece goes down, that's the end of the talk. Okay. All right. So let's do the characters of the additive group, by which I mean homomorphisms, continuous homomorphisms from the additive group to the circle, not to C star, but to the circle. We'll see why. And we'll do what are called the quasi-characters of the multiplicative group. So this is KV star plus, local characters, by which I mean homomorphisms continuous to C star. And we're going to need both to do this functional equation and things like that. Okay, so what about the additive characters? Well, let's start with the real numbers. So the characters of the additive group are parameterized by real numbers, right? Because we saw that, so we have one, let's call it phi infinity of x is equal to e to the minus 2 pi I x. You're going to see immediately, or pretty soon, why I chose this minus sign. And then that's one character of the real numbers. And I get other characters by multiplying it by y. So I also have psi y of x is e to the minus 2 pi I xy for all y in R. R is its own Pontryagin dual. So I get a character for y equal 1, which is this. And all of these characters have the property that on the integers, well, this is trivial on the integers, which is one reason I've taken y to be 1 there. What about multiplicative characters? Well, any multiplicative character of the real numbers, I of t, is of the form absolute value of t to the s times the sine of t to the epsilon, where s can be any complex number and epsilon can be plus or minus, and it can be 0 or 1. So the characters of the positive real line, positive real numbers are just complex numbers given by t to the s, but if I have a real number, I can also take it to its sign. So those are all the characters of the multiplicative group of R star. And what about C star? Well, psi of C star, if KB is C, I have the character psi v, which is e to the 2 pi I, or maybe minus 2 pi I forgot which one I like, times the trace of z. So if I trace down to the real numbers, I can take that, and I can also multiply it by, I also have psi y of z is e to the minus 2 pi I, the trace of yz, and for any complex number, c, and that gives an identification of c with its own quadrinomial dual. And what about multiplicative characters? Well, that's much more interesting, because for the complex numbers, I have characters like this. You can take z over z bar, and you can raise it to any power a, which is a half integer. I'll show you what that even means, times the absolute value of z to the s power. So first you can map z, this complex number, down, right? I mean, you have maps from c star to r star plus, and you also have where the kernel is the circle group. And these are the characters of the quotient group. And you also have characters which are maps from the circle to itself. And by this I mean, you could write this as z to the 2a, let's see, multiplied by z bar over z bar to the a. So this would be z to the 2a divided by z bar to the a. So that makes sense for any, first of all, this is of absolute value 1, so you can raise it to any integral power, but you can also you could interpret it this way, and that allows you to raise it to any half integral power, right? Because this is now an integer, so you can make it to the 8th power, divided by that, that's the character of the circle. So these turn out to be, it turns out there are many more interesting characters of the multiplicative group of complex numbers than there are of the real numbers. Here you only have a choice of sign, here you have a choice of half integer. And what about finite fields? Well, finite fields, if we have a homomorphism from kv star to c star, for the same reason as the dells, this has no small subgroups, so this, any homomorphism chi must be trivial on some neighborhood 1 plus pi to the n of n, for some n greater than equal to 1, n greater than equal to 0, where for n equals 0, you interpret this as a star. And you call that n, the first n where it's trivial, the conductor of chi. And if the conductor is 0, then chi is a character of k star on a star, trivial on a star, and that's the powers of pi, so it's determined by chi of pi v, which is just some complex number. So for any complex number, I can get a character of k star mod a star by defining this. And those give what are called the unramified characters. And if it's not unramified, well, it's certainly trivial on something like this, and then it's determined by this chi of pi v and chi, the values on the units, which are in the finite group A star modulo this group. Okay, now additive characters. Suppose I did QP, what would be my additive character of QP? Well, again, there you get characters of all orders because you don't have a maximal compact subgroup. So let's just try for KV equal to QP. I get an additive character as follows. I'll call it 5P, or X. I look at X, and it has some finite denominator plus something I just write it as e to the 2 pi I x. Well, what the hell does that mean? Well, I view via the fact that QP mod CP is equal to the p to the n torsion in this bigger group Q mod z, which are sort of all the torsions. This is, right, this is the limit of z mod PBA z, and this is the limit, the direct limit of z mod n z. And the p torsion just turns out to be this group. So I can get a character of this by viewing it as a subgroup of this, and if I have an element in Q, well-defined mod z, then this number makes sense, right? And so that gives me a character of QP trivial on CP and not trivial P inverse on CP. Because if I take X to be 1 over P, this is a P through to unity, right? Now notice, now you can see the brilliance of my choice of sign here. Namely, if I consider the character of the adels, that's given by the product of all these things. So consider the adels of Q, which are the product of R with the restricted product over ZP, QP, the additive group. I can define psi A to be the product, well, to be my psi infinity cross the product of all my psi p's, where I call this thing psi p. How do I do that? Namely, for any adel, right, I evaluate this by evaluating this character on the real component, and then on the finite components, almost all of them are in ZP, on which this character is trivial. And the ones that have denominators, this character gives me some p power root of unity, and I multiply all those roots of unity, and I get the value of psi on the adel. But notice that since if this is a rational number, then I get e to the minus 2 pi I times the rational number here, and I get e to the plus 2 pi I times the p primary component of the rational number there, and if I take the product over all p, I get the same rational number, so that this character of A is trivial on Q. So it's a character of this compact group, A mod Q. Right? And moreover, I get other such characters by taking, for a rational number B in the rational numbers, I can define psi B of X for an adel X to be psi A of Bx. And the same thing works. Namely, if X is a rational number, so is this. So it's another character of A mod Q. And it turns out that gives all the characters of A mod Q, namely the Pointryagin dual of this compact group A mod Q is Q, which is a discrete group. And that's another crazy way of defining the adels. That's how, in some sense, the Russian school tumbled on the adels. Gelfand was interested in the question of what is the Pointryagin dual of Q. And if you know Pointryagin duality, that says it has to be A mod Q. So that doesn't quite define the adels, but at least it gets you this quotient of it. Okay, just from duality, just from topological group theory. You start with this topological group with the discrete topology, and you ask what's its Pointryagin dual. And it's complicated, but you get this group. Okay, that's a good time to stop, and we'll take up on Tuesday with the characters of the edel classes. This is a character of the adels trivial on Q. We want more characters of the edels that are trivial on the rational multiplicative group, just like the norm character. We'll work those out next time. By Thanksgiving, by the way, I think it's perfectly reasonable if you tell me what your paper is going to be like. Because if you haven't got a paper topic by Thanksgiving, you probably won't have a paper topic in time for me to give you a grade. So if you want a grade for this course, just by the end of next lecture, because we won't have a lecture on Thanksgiving. Thanksgiving is Thanksgiving. We won't have a lecture next Thursday, but on Tuesday at the end of the lecture, if you could just bring up, a tentative title and a one-paragraph summary of what you're going to cover. That way I can take a look at it over Thanksgiving break and warn those of you whose topics are ridiculous, that your topic is ridiculous. Anytime, okay? And it should also have your name on it. You know, name, topic, abstract. Good? Okay, great.
What topic is ridiculous?
Pardon?
What kind of topic is ridiculous?
Oh, you might say, I'm gonna do the Langland's correspondence in automatic form, or something. That just would be, by ridiculous, I mean too big.
I see.
Or it might be too small, like the proof that the integers are a principal. I want something in between. Okay, less than or equal to that, greater than equal to that. Okay? Great.
So we have that, I think you mentioned something about Z is discrete and R and the by quotient and the other way around, because that is local stuff.